The idea that every volcano on Earth could erupt simultaneously is a popular yet physically impossible scenario. Volcanoes are tied to tectonic plates that move independently at different speeds and directions. There is no central mechanism that could synchronize them. Furthermore, volcanoes operate via local plumbing systems. Magma reservoirs are isolated and lack a planetary master switch to trigger a simultaneous event. In summary, Earth's geological systems are too disconnected to support a synchronized eruption. The planet's resilience is built into its decentralized structure. Volcanoes are not globally linked systems. They operate as isolated geological features, driven by independent tectonic plates. Consider the Pacific Ring of Fire and the Mid-Atlantic Ridge. They are powered by entirely different magma reservoirs and plate boundaries. Because they reside on different tectonic plates, the immense pressure and seismic triggers for one cannot be transmitted across the globe instantaneously. Tectonic isolation ensures that volcanic events remain localized, maintaining the planet's structural stability. If we imagine a global eruption scenario, the primary threat shifts from local lava flows to the atmosphere itself. Millions of tons of sulfur dioxide reach the stratosphere, where they convert into sulfuric acid aerosols. These tiny particles act like a planetary mirror, reflecting incoming solar radiation back into space. This process leads to a significant global temperature drop, creating a lasting climate impact. A volcanic winter occurs when massive sulfur injections into the stratosphere form sulfate aerosols. These aerosols act like a global mirror, reflecting solar radiation away from Earth, leading to a sharp drop in planetary temperature. The result is a period of rapid global cooling that can persist for years. Even moderate temperature dips significantly alter global weather patterns. The agricultural consequences are devastating. Sunlight reduction halts crop growth, destroying essential food chains and leading to widespread food insecurity and famine. Ultimately, a volcanic winter represents a far greater threat to human civilization than the immediate physical destruction near the eruption sites, as it undermines the global food supply. The tephra blanket is a severe global threat. Massive volumes of ash and rock fragments injected into the atmosphere would create a catastrophic debris field. Aviation would ground instantly. Volcanic ash melts in jet engines, causing catastrophic failure. Global air travel would halt, leaving the skies silent. Water filtration systems would fail as ash clogs essential infrastructure. Meanwhile, power grids face collapse under the weight of wet, conductive ash, severing modern communications. With power and transport gone, global supply chains would disintegrate, cutting off access to food, medicine, and critical resources. The Toba supereruption, which occurred 74,000 years ago in Sumatra, provides our most significant historical data point for massive climatic disruption. This event serves as a benchmark. Scientists model extreme outcomes by analyzing how Toba's sulfate aerosols triggered a years-long global cooling period, often called a volcanic winter. By studying Toba, researchers can better simulate the consequences of simultaneous eruptions, helping us understand planetary resilience when faced with massive atmospheric shifts. While the idea of all volcanoes erupting simultaneously is a myth, volcanologists actively monitor for a very real and dangerous phenomenon known as a volcanic cascade. A volcanic cascade occurs when one major eruption triggers secondary events in nearby, interconnected magma reservoirs. This happens because subsurface conduits often share pathways. Unlike global events that require planetary tectonic shifts, cascades are localized. One system destabilizes another through pressure changes within shared fault zones or rifts. Scientific consensus confirms that the Earth's crust is too diverse for global synchronization. Volcanic monitoring focus remains on these specific, high-risk, interconnected chains. The hypothetical scenario of a simultaneous global eruption overlooks the fundamental resilience of our planet. Earth is not a monolithic structure, it is deeply heterogeneous. Geological systems operate in distinct magma reservoirs. The Earth's crust and mantle are too fragmented to ever support a planetary-scale master switch for volcanic activity. Today, we rely on the global seismic network and advanced AI forecasting to monitor Earth's health. These tools show no signs of the instability required for a simultaneous event. Scientific consensus confirms that volcanic systems are independent actors. Earth has survived massive events in the deep past, proving its robust long-term ability to regulate and recover. Our planet's resilience is our greatest safeguard. We are currently in a stable tectonic state, far removed from any catastrophic global upheaval.